Greetings and welcome to lecture series on thermodynamics. We started with availability or exergy in last lecture and will continue with the derivations. We have seen the concept of exergy. So basically exergy is the property that quantifies potential for use. We had seen the difference between high grade and low grade energy. So work is high grade energy and heat is low grade energy. We have seen the reason for this. Then we had seen dead state. What do you mean by dead state? When system is in thermodynamic equilibrium with its environment. So that is known as dead state, and dead state properties we had discussed. It is denoted by subscript 0, so T0 and T0. Next we have seen definition of availability, and the availability value cannot be negative. It can be 0 or it can be greater than 0. Okay, it cannot be negative. And like entropy is what? Energy remains constant. Entropy is what? Generated. While exergy is what? Destroyed because of irreversibility. Unavailable energy we had seen, which is equal to TODS of universe. So based on this equation, we will be able to solve a lot of numericals. I is equal to TO into delta S of universe. So basically you can see from this equation that the unavailable energy, it can be calculated by calculating change in entropy of universe. Means entropy formulas also you will be using in this module. Then after that we have seen available energy referred to a cycle or heat transfer from infinite reservoir. So whenever heat is transferred from high temperature source T1 amount of heat, the temperature of source doesn't change. That we had seen. So the final equation was W max, means available energy is W max available energy is equal to Q minus TO ds. Okay, and also you have to remember this equation. Let me highlight this equation. We will be using this equation in numericals also. Q in bracket 1 minus T0 by T. Okay, T1 or T, you can remember this. Now next derivation is availability of non-flow or closed system. So we have studied two types of system, closed system and open system in module number 1. So we will derive the equations for closed system and open system availability, very important derivations. Okay, so what do you mean by closed system? Closed system means mass doesn't transfer, but energy transfer. So here I have given example of closed system. A cylinder and piston arrangement is given, and this is the closed system. There will be a gas inside whose pressure is P1, temperature is T1, internal energy is U1, and so on. So subscript is 1. Now there will be surrounding over here. Okay, so surrounding subscript is what? Dead state, na? It will be 0. So surrounding, you can visualize over here that I have shown pressure P0 acting on the piston. Why? Because whenever there is expansion, now what will happen is the expansion process is against the surrounding pressure. Are you following this? See, suppose there is we are supplying heat to the cylinder, to the engine. Okay, you can visualize the engine, bike engine. Okay, so what we do, we burn fuel, we supply heat to the engine. Okay, we get work, and some heat is released from the engine. Okay, so engine gets heated up, and either by radiator in car, and in case of bike it is natural convection, heat is rejected from the engine. So same thing you can see over here. This is a closed system, and from here you can see that heat is being rejected and we are getting some work. Now this work is against what? Atmospheric pressure. That is why I have shown over here it is against P0 pressure. Okay, I hope this diagram is clear. Now what is done is, whatever heat is rejected from this engine, it is supplied to the Carnot engine. Okay, and we get some work from this engine and some heat is rejected. Now this heat which is rejected we have already discussed in previous derivation. It is T0 S1 minus S0, which is unavailable energy. Okay, you can go through last lecture. We have seen that this heat rejected is what? T0 S1 minus S0. Provided that the Carnot engine is operating between this Q and surrounding temperature T0. Okay, now what we can do is we can apply first law of thermodynamics. Okay, so we will apply first law of thermodynamics undergoing a process. So what is that? We have already seen this. Delta U is equal to Q minus W. Okay, so we'll apply first law of thermodynamics for this one. Okay, so let me highlight this. Okay, so we'll apply to this system first law of thermodynamics. So this is the system. We'll apply first law of thermodynamics to the system. So what we will get is delta U is equal to Q minus W. Okay, so delta U is equal to Q minus W. Now W which we are getting, it is we are denoting it by W fluid, work done by the fluid present in the system, like that. Okay, so now what is delta U? This piston is the gas is expanding, and inside pressure and temperature, okay, it will reduce. Okay, it will go to dead state. So what is final internal energy? U0. So delta U means what? Final internal minus internal energy minus initial internal energy. So U0 minus U1 is equal to, now here you can see from the system heat is rejected. Q, you can see it is going outside the system. That is why it will be what? Minus Q. And work is done by the system, so sign will remain as it is. Okay, so it will, even though here it is minus W, we are seen that this actual work, it is positive only. Okay, when work is done on the system, we will take one more negative sign, and negative will become positive. Okay, so in this case U0 minus U1 is equal to minus Q minus W of fluid. So what will be W of fluid? W of fluid, take this on this side, so you will get U1 minus U0 minus Q. Okay, now what is the work done by the engine? Okay, so this was the work done by fluid, which we calculated in previous slide. Now we will calculate what is the work done by the engine. So this derivation we had already seen. Okay, what is the available energy? It will be, we have already seen this part. Okay, so it will be heat supplied minus heat rejected. Heat supplied is Q and heat rejected is T0 S1 minus S0. And this derivation we had already seen. So work done by the engine is Q minus T0 S1 minus S0. Now what will be the maximum work? Maximum work will be W of fluid plus W of engine. We have two works over here. So W of fluid plus W of engine. So sum of W of fluid and W of engine will give us maximum work. So add both the works now. Okay, so here you can see W max will be equal to what? W of fluid plus W of engine. What was W of fluid? Recall it. It was U1 minus U0 minus Q. And what is W of engine? It is this one, Q minus T0 S1 minus S0. So now you can see over here, this Q and this Q will get cancelled. Okay, why? Because it is negative and positive. And what you will get? The equation which you will get is, it will be this one. Okay, U1 minus U0 minus T0 in bracket S1 minus S0. Now we will take this concept which I had discussed before. When the piston is moving towards right, Okay, when we are getting this W fluid has to overcome the pressure of atmosphere. It is not working in vacuum. So there will be some resistance by the atmospheric pressure. Okay, so the piston moving outward has to spend a work in pushing the atmosphere against its own pressure. So this work is being opposed by the atmospheric pressure. This work, which may be called as surrounding work. Okay, so this surrounding work is what? P0 V0 minus V1. Okay, so it's like PDV. So P0 V0 minus V1. Now what will be the next slide we will see. Okay, so let me clear this.
Sir.
So now we are seeing two equations.
Yes, sir.
First is maximum work W max, which is W of fluid plus W of engine. This equation we have already seen. You have to remember this equation. Okay, this equation we will be using in deriving a function. Okay, so this equation we will be using later on again. And what is surrounding work? P0 V0 minus V1. Okay, so this we have already discussed in previous slides. So what will be the maximum available useful work? It will be W max minus W surrounding. Why? Because this surrounding is opposing the motion. Okay, so useful maximum work will be W max, which is W fluid plus W engine minus W surrounding. Now what is this W fluid plus W engine? It will be U1 minus U0 minus T0 in bracket S1 minus S0. We have already derived. Minus what is W surrounding? It will be P0 V0 minus V1. So arrange the terms. You will get U1 plus P0 V1 minus T0 S1 in one bracket minus of this term. Okay, now first bracket. So we will here you can see that this U1 is capital. Okay, so it is internal energy. Similarly, here you can see V1, it is capital, means it is volume. S1, it is capital, means it is entropy. So on unit mass basis, we will get small w useful max, it will be small u1, specific internal energy plus P0 specific volume minus T0 specific entropy minus specific internal energy plus P0 specific volume minus T0 specific entropy. Okay, so now this bracket, first bracket, it is denoted by phi1 minus second bracket, it is denoted by phi0. So this is the equation which you have to remember, formula availability of closed system or non-flow system. What is that? W useful is equal to phi1 minus phi0. Okay, now what is this phi? What is this phi? Where phi is per unit mass. Okay, you have seen this is per unit mass basis. It is known as non-availability function and it is composite property of both system and surrounding. So what is system? System is at T1 T1 properties, and what is surrounding? It is at subscript 0. Okay, so this non-availability flow function, which is phi1 and phi0 of this phi, it is a composite property of both system and surrounding. So this was the derivation of available energy for closed system. Now we will go to the steady flow system, or it is also known as open system. So first understand this diagram. So what is shown in the diagram? This is a system. So a stream of fluid is flowing inside the system. It has some energy. So pressure is P1, velocity, volume is V1, and temperature is T1. Then we are getting work Ws, and outflow is there, P0, V0 and T0 is there. So what will be the steady flow energy equation? Q minus W is change in kinetic energy plus change in potential energy plus change in enthalpy. Okay, now from this system some heat is rejected and whatever heat is rejected, it is used to drive a Carnot engine. So we will get WEng work from that Carnot engine, and heat rejected, again it will be similar to previous case, it will be T0 S1 minus S0, provided that the sink is at surrounding temperature T0. So since heat is rejected, for this equation Q will be negative, and since Ws is output from the system, it will be positive. So it will remain negative only. Okay, so negative, it won't be positive like that. So this equation, if you see now, since Q is rejected by the system, it will become negative. So minus Q minus Ws is equal to, now we will neglect change in kinetic energy and change in potential energy. So what you will get if we neglect this part, okay, what you will get is minus Q minus W is equal to delta H. Okay, but there should be proper justification for neglecting change in kinetic energy and change in potential energy. When we are solving numericals on availability of steady flow system, we will see that in one numerical we don't neglect this delta kinetic energy. So whatever derivation we do now from this side, it is neglecting change in kinetic energy and change in potential energy. So that equation, when you want to use where there is change in kinetic energy, you need to consider this change in kinetic energy separately. Don't forget about that. Okay, you should remember that when we are doing this derivation, we are neglecting change in kinetic energy and change in potential energy. But there is one numerical where we will see that there is change in kinetic energy. In such cases, that formula you should take care of change in kinetic energy also. So remember this point. Okay, so we are neglecting this. So what you will get, just shift the terms, take Ws on this side, so it will become positive. So Ws is equal to minus Q minus delta H. Now what is this delta H? It is final. What is the final state? Dead state. So H0 minus initial state is H1. Now since this is minus delta H, it will become H1 minus H0. Okay, because this is negative delta H minus Q. So this is the equation of Ws. Now we will calculate the equation of W engine. So what will be W engine? Heat supplied minus heat rejected. So the heat rejected by the system may be used to run a reversible heat engine, which is Carnot engine, and output from this engine, W engine, will be equal to, we have already seen this equation, Q in bracket 1 minus T0 by T1 equal to Q minus T0 ds is equal to Q minus T0 S1 minus S0. Now we have two work, Ws and W engine. We have two work. Okay, so let me write down the equations again. Ws was this equation, W of engine was this equation. So what will be the maximum available useful work? It will be addition of these two works. Okay, so W max will be Ws plus W engine. So Ws is what? Ws is this part, H1 minus H0 minus Q, H1 minus H0 minus Q. What is W engine? W engine is this part. So W engine I have written over here. Q minus this equation. Q minus T0 S1 minus S0. Okay, in bracket. So now just arrange the terms. So here you can see, let me clear this part. You can see that this Q and this Q will get cancelled, and arrange the terms properly. You will get that H1 minus T0 S1, H1 minus T0 S1 minus in bracket H0 minus T0 S0. Now this first bracket is denoted by psi 1 minus this second bracket is denoted by psi 0. So what is psi? In general, what is psi? It will be H minus T0 into S. Now this psi is known as steady flow availability function. What was phi? Phi was availability function of closed system. Okay, and this is what steady flow availability function, psi. It is also known as Keenan function, and it is also a composite property of system and surrounding. Okay, so surrounding has subscript 0 and system has subscript 1. So we have completed now. So let me quickly go through the things which we have completed today. What all things we have completed today. So we had seen first part, first equation, first derivation was this one, heat transfer from finite reservoir where temperature reduces. Okay, in this case what we had got is W max was Q minus T0 ds. Okay, then we have seen whenever there is heat transfer through finite temperature difference, there is loss of available energy or decrease in available energy or increase in unavailable energy, and that value is T0 delta S dash minus delta S, this area. Okay, then we have seen the derivation of availability of non-flow or closed system. What was the equation? Equation was, this derivation is very important, you have to remember the derivation. W useful is phi1 minus phi0, and what is phi1? This value you have to remember. Okay, this terms you have to remember. Then availability of steady flow systems, we have derived this equation, W max is psi1 minus psi0. Now one important thing you have to remember, this equation, let me highlight this equation. This equation we have derived neglecting change in kinetic and potential energy. Okay, if in question data is given, there is some change in kinetic energy, suppose velocity and this height is given z, in that case you have to consider, we have to add here. Okay, the formula will change. How the formula will change, we will see in numerical. Okay, when we see the numerical, we will see that. Now next topic, Helmholtz function. Okay, so very important function. Now there will be two functions, one is Helmholtz function and second one is Gibbs function. So these two functions we will be using in next part as well. Okay, so after this availability module, we have a module of property relations. There also we will be using this Helmholtz function equation. Okay, now what is this Helmholtz function? It is defined as, it is a property relation between which property is internal energy minus temperature into entropy. Okay, so we'll see what is the concept behind this Helmholtz function. So while deriving availability of closed system, we had seen this equation. W max was, this was before subtracting the surrounding work, W of surrounding. So W max was what? W of fluid plus W of engine. We got this equation. Okay, now what is Helmholtz function F? It is U minus Ts. So for a system, what you can write, for two equilibrium states operating between the state I and F at same temperature. This is very important, at same temperature, that is why I have highlighted by red. So Helmholtz function, we have to, it is related with same temperature. So in this case, what you can write is, this function you can write between state I and state F, difference. So Fi minus Ff at constant temperature equal to Ui minus Uf at constant temperature minus temperature is constant, that is why only T is there, not delta T, in bracket Si minus Sf at constant temperature. Now if you compare equation 1 and 2, compare this equation 1 and 2, right side is same, means you can say that right side is same. So what you can say, W max, this term will be equal to what? W max. Okay, so this term will be equal to what? W max. But what do you mean by W max? W max means maximum you can get that work, or you can, in actual case, you can get less than W max. So now we need to write an equation. Okay, so what we will do, compare equation 1 and 2. From 1 and 2, what you can write is W is less than or equal to Fi minus Ft when temperature is constant. Now this Fi minus Ft is what? Fi minus Ft is what? This is W max. Now see the logic behind this equation. W will be less than W max, so actual work will be less than W max, or W can be equal to W max. In this way I have written this equation. So comparing 1 and 2, I can write equation in this form, that W is less than or equal to Fi minus Ff at constant temperature. Now here you can see Helmholtz function, we are not writing Ff minus Fi. It is not final Helmholtz function minus initial one. We are writing initial minus final. Means Helmholtz function value is decreasing. Okay, so this value is what? Decreasing, Fi minus Ff. So based on this equation we will make a conclusion. So W is less than or equal to Fi minus Ff at constant temperature. So what I can say is the work done by a system in any process between two equilibrium states, we have taken example of equilibrium states as I and F at same temperature. So here you can see after bracket temperature is same, during which system exchanges heat only with the environment, is equal to or less. So this work is equal to or less than decrease in Helmholtz function of system during the process. So you can see this W is less than or equal to decrease in Helmholtz function. Fi minus Ff means what? Decrease in Helmholtz function. Now when you will get the maximum work, W will be equal to W max, then process is reversible. Then process is reversible, and then you will get equality sign. If the process is irreversible, then W will be less than Fi minus Ff at constant temperature. Next function, Gibbs function. So Gibbs function, it is denoted by G, and again it is a difference between the two properties H and Ts. Okay, now why we use this function is because see, every time when you are writing a mathematical equation, whenever you get H minus Ts, okay, equations are very big. You cannot always write H minus Ts everywhere. So what we do is to simplify the work, we write H minus Ts as G. Okay, it's like simplification. So that G is known as what? Gibbs function. Now we have to go back to the derivation of closed system of availability. What was the useful maximum work? It was W max, which was W of fluid plus W of engine minus W of surrounding. So we had got that this was phi1 minus phi2. Okay, if you remember, this is not phi1 minus phi2 because this is internal energy, but when you write it in per unit mass, you got that phi1 minus phi0. So what if I rearrange this equation, U1 W useful max, if I rearrange the equation, I am not going through that, you can see the video and you can understand this. So when you rearrange the equation, you will get this W useful max as like this. Okay, this will be the equation. Now you can write it as, suppose the final state, suppose initial state is I. Okay, suppose initial state is I and final state is F. Okay, and here when we had derived it, I was the initial state and O was the dead state, means final state. So you can replace 1 by I and 0 by F. Okay, subscript, so that you will get this equation. So W useful max will be Ui minus Uf at constant pressure and temperature. Now remember this, Helmholtz function was at constant temperature. Now this is at constant pressure. Why? You will see over here. Plus pressure. Here you can see there is not delta P. You don't have delta P. So P, Vi minus Vf, pressure and temperature is constant, minus T, Si minus Sf, pressure and temperature is constant. Now if you see Gibbs function, G, what is G? G is H minus Ts. Okay. Now what is the definition of this enthalpy? Enthalpy is internal energy U plus flow energy PV. U plus PV. So I have replaced enthalpy by U plus PV, and minus Ts will remain as it is over here. Minus Ts will remain as it is. Now what we can do is, for two equilibrium states I and F at same pressure and temperature, what we can write? We can write Gi minus Gf. Okay, so Gi minus Gf will be Ui. Okay, see this equation. Okay, let me clear this. Okay, see this equation. See this equation of G. So Gi minus Gf will be equal to Ui minus Uf when pressure and temperature is constant, plus T Vi minus Vf when pressure and temperature is constant, minus T Si minus Sf when pressure and temperature is constant. Now if you compare equation 1 and equation 2, useful maximum work right side and Gibbs function difference between initial and final state, both are same. Okay, so right hand side is same. So similar to the Helmholtz function, what you can write now? What you can write is, from equation 1 and 2, you can write that W useful is less than or equal to Gi minus Gf when pressure and temperature is constant. Okay, now this Gi minus Gf, according to equation 1 and 2 is what? W useful, but it is maximum. Now see this logic. W useful is equal to W U max when process is reversible. But when process is irreversible, then W useful, which is actual useful work, will be less than the maximum work. This is the logic behind writing this. W useful less than or equal to initial Gibbs function minus final Gibbs function when pressure and temperature is constant. So again, useful work is less than or equal to Gi minus Gf when pressure and temperature is constant. So similarly, we will write down a statement as we had written for Helmholtz function. But in this case, pressure and temperature is constant. So decrease in Gibbs function. Gi minus Gf means what? Decrease in Gibbs function of a system sets an upper limit to the work. Upper limit means what? If this is reversible, then it will be maximum work. Like that. It is upper limit. Exclusive of PDV work in any process between two equilibrium states. What are the equilibrium states? I and F at same pressure and temperature, so P and T, provided the system exchanges heat only with environment which is at same temperature and pressure as the end states of the system. Okay, so end state is equal to environment state. Okay, now if the process is irreversible, useful work will be less than the W useful max. So this W useful will be less than Gi minus Gf when pressure and temperature is constant. Next topic is second law efficiency or effectiveness. So what do you mean by second law efficiency and effectiveness? So let me ask you a question. There is a source, there are two engines. So this you have to answer. There are two engines. So one engine, it is operating. Okay, let me show work over here. Okay, there are two engines. one engine is operating between source 600 Kelvin and sink is 300 Kelvin, and second engine you can see, engine B, it is operating between a source 1000 Kelvin and sink 300 Kelvin. Now actual efficiency of the engine A, if you see, it is 30%, and actual efficiency of engine B is 30%. Okay, assume this. So both the engine is having same efficiency. Now my question to you, you have to think about this. My question to you is, which engine is having more efficiency? Okay, so which engine is actually having more efficiency? Now to understand this, what we will do, we will use Carnot efficiency. Okay, so Carnot efficiency, what is that value? It depends on only temperature limit. So for engine it is T high minus T low upon T high. Okay, so when I substitute the values of source and sink for A and B engine, what I get is, you can see in this diagram also, efficiency maximum or Carnot efficiency for engine A is 50%, and Carnot efficiency of engine B is 70%. Now my question to you is, you have studied two types of efficiency. First efficiency is this one, which is thermal efficiency, which is output means W upon heat supplied Q. Okay, now when you consider Carnot efficiency, the Carnot efficiency value is 50%, means engine A and engine B, these two engines are which type of engine? These are not Carnot engines. These are which engines? These are which engines? These are actual engines. So engine A is also actual engine and engine B is also actual engine. Why? Because actual efficiency is less than Carnot efficiency. Now the question arises over here is, which engine is more efficient? Problem is that. Okay, why? Because thermal efficiency of both the engine is same. Okay, it is 30%, and maximum efficiency of engine B is more. Okay, so you can think about this problem, and I will answer this problem in the next lecture. Okay, so which engine, actual engine A and actual engine B, which will be the more efficient engine and why? Okay, so basically answer lies here in the concept of second law efficiency or effectiveness. So we will be defining one more type of efficiency, and with the help of that only we can answer this. So what you can do based on your logic, now you can try to think about this answer, and we will see what is the